Matt. I'm part of the cloud engineering group, focusing on integrating low-level virtualization components with OpenStack. But today, I'm going to talk a bit about what are the different kinds of live block device operations that QEMU has to offer to solve different kinds of problems. First, we'll set a bit of context, and then we'll see what they are, where they're used, and how they can be combined to solve certain practical problems. I assume most people in this room are familiar with QEMU, but we'll do a bit of background as well. Just show of hands, how many have heard of QEMU in this room? Okay, pretty much everybody. First, we'll set a bit of context for virtualization stack, KVM-based, for the benefit of those who aren't familiar. I assume most of them are. And then we'll see a small primer on how to operate a QEMU instance. Followed by that, super quickly, we'll see how different block devices, or block devices in general, are configured in QEMU. And finally, we'll see the different block device operations, long-running ones, potentially long-running, to do various kinds of neat things, and the practical use cases for them. All right, so that's a typical KVM virtualization stack. You see at the bottom, Linux kernel module KVM as a character device exposed to QEMU, which will operate it via ioctls. And then sitting on top is QEMU, which is your guest as a complete process, just like any other process on your host. So QEMU exists alongside those processes, and you can use regular tools like top, PS, and so forth to monitor the various details. But launching QEMU with long command lines can get super tedious. If you ever seen libvirt-generated command line, it goes into pages and pages. Well, not really pages, but sufficiently long. So you don't really want to launch QEMU by hand, although there are some cases where people do that. So this is where libvirt comes in as a hypervisor-agnostic library that provides neat abstractions and other things for the life cycle of a virtual machine. And that's the libvirt daemon. And even higher is the projects like OpenStack, where it operates various instance launching processes via its virt driver interface connecting to libvirt, which in turn talks QEMU, and the complete back and forth goes on from there. And even the more recent entrants, like KubeVirt, also relies on libvirt, but not exact same architecture, but some of the core fundamentals remain. On the far left, you see libguestfs, probably far right too, libguestfs project, which is a neat tool, which you haven't heard. It's actually a set of tools that provides various utilities to do different kinds of things on your guest images, to safely access them, resize, and launch templates. It does a whole bunch of things. It also uses QEMU and libvirt also in various of its tools to give you different functionality. So in this talk, we'll zoom into the QEMU's block layer and see what functions it has to offer and what practical use case it solves. Most of the times, these features are already exposed via high-level libraries like libvirt, or even higher-level management software like Overt, OpenStack, and so forth. But sometimes it can be instructive to look under the hood to see what's happening, especially it helps you during debugging. QEMU's block subsystem offers a bunch of things. To begin with, a guest-visible emulated storage devices like your SCSI, IDE, or para-virtualized drivers where the guest knows that it is being virtualized, like Verde SCSI or Verde block. If you run that command on top, you see, and you look for the storage devices section, you see different kinds of devices that QEMU has to offer. So that shows you a nice picture of what all the tools it offers. And then QEMU's block layer and QEMU in general is written in layers, and there's a lot of code reuse between components. And QEMU offers different types of block drivers. One is a format driver where how data is interpreted on the host, and that's a protocol driver actually, where how QEMU interprets data on the host. And the format driver is where you recognize one of the popular names is the QCOV2, that QEMU's native image format, and VMDK and other formats that QEMU has to offer. But the native format is QCOV2, most people recognize. And for the protocol driver, you see things like Ceph or network block devices and so forth. It also offers different live operations that you can do on block devices, also offline. The most popular is QEMU IMG, which you can use to create images, create backing chains, convert from one format to another, and a bunch of other whole things. And yeah, the live operations are where most of the interesting stuff happens. Also, equally interesting stuff happens offline, but people care in production stuff that runs in live. QEMU's copy and write overlays, as most would know, offers a way to refer a base image that has, say, for example, a Fedora operating system, and then you can create an overlay based on that base image, where this overlay refers to that base image, and you can do all kinds of things, destructive things in this overlay. And then, if you screw up something, you can discard it and go back to the base overlay. Base image. So in this kind of setup, the base image can be of any format, but the overlays are always QCOV2. So there's different kinds of terminology I'll use throughout in the talk. Not one kind. The thing is called base images and overlays. When I say overlay, it is always the image that is created based on the first image in a disk image backing chain. So we'll see what they are. So when you have a simple backing chain like this, the first, whenever QEMU tries to read a cluster, it reads from the existing overlay, if it is allocated. Or else, it will traverse the backing chain and read from the other, the base image. And then QEMU does some caching and so forth. But all the writes happen on the overlay image. There are several use cases to it. The one I just mentioned is this, a thin provisioning is where the Fedora image is there, base image, and then you can create multiple overlays based on it, so you can give out different thinly provisioned disk images to users. And snapshots and backups. We'll get to that. So how do you create this minimal backing chain? You see that command line over there, and I especially highlight on the bottom one. So first command line creates the base image. The second one creates the overlay. And why do I highlight the base image formats and the base image file? If you don't specify the backing, the format of a raw image file, QEMU will probe it. So that is a potentially CVE waiting to happen. Why? Because a malicious guest can write a header that can look like QCOV2 and can corrupt the image. So you don't want that to happen. So that's why it is recommended to explicitly specify the backing file format and the backing file, of course, with those options. Sorry. Another thing to keep in mind is when QEMU is already using a disk image, you don't want external processes to access them, potentially corrupting. So to mitigate that, QEMU already offers existing runtime commands called monitor, QMP monitor commands that you can do. For example, if you want to live resize a guest, that QEMU offers something even to change backing files and various other functionality. So you don't want to do that. And also, alternatively, I mentioned the libguestfs project. That also offers a tool called guestfish that will let you safely, in a read-only manner, access the disk image and examine its contents. So for example, if you're using a Fedora-based operating system and you mess up SC Linux labeling in it, so you can use this tool to fire up the disk image and fix that stuff. And again, you can make the image bootable. So feel free to ask questions if there are any. And in more recent versions of QEMU, it offers disk image locking. So this essentially prevents you to shooting yourself on your foot by not letting two processes writing to the same image. So to that end, it uses the recent Linux locking mechanism, the open file description locks. And as a quick example, we won't go into the details of these things here because I wanted to mention it for completeness, and this is a new feature where users may have to take explicit action. So to query an in-use disk image with recent QEMU versions, 2.10 or whatever, so you have to specify the force share option. For example, if a disk image is already in use, the foo.qcow2 file, and you want to query it for read-only information, you supply that force share flag, then a read-only access is allowed to that while writes are happening. Now, there's some cases where you can get stale information when you're doing read-only access of that image. Why? One example could be if QEMU is accessing, actively resizing the disk image, and you try to query for information, so you see inconsistent results. So insofar as you're aware that information can be stale sometimes, you can use this. And there are some valid cases, like in QEMU IMG info falls under an area where you can safely query an in-use image. So yeah, I just wanted to highlight that there. For example, OpenStack uses this knowingly that there can be potentially stale data because it runs this command in a loop so that if it even misses the information, it will catch up again on the next run. And on the recent QEMUs, the same locking mechanism can be specified by the, when you configure block devices, there's a locking option. So it defaults to open file description locks if your Linux kernel supports. Otherwise, it defaults to POSIX locking. I'm not quite sure, but there's some block people here can confirm. But that's what, from my quick look in the code, that's what it looks. So yeah, so there's that. So in this part, we'll see how do you operate a QEMU instance, like especially tools like libvirt, and how it can send various commands to modify an image, or send query commands, or modify the state of the VM, how those kinds of things are done. QEMU offers this QEMU machine protocol where it's a JSON RPC interface through which libvirt interacts and sends back and forth commands to do various things. So you can send query commands to query what is the status of migration, for example, or if there's a long backup operation going on, hey, can you tell me how much more information to be copied, and existing block device jobs in progress, various things like that. So to get a sense of where this QMP is configured, if you look at the libvirt configured QEMU instance, you see a lot of command line that is snipped out, but focus on the caret setup where it sets up a Unix stream socket for back and forth communication with QEMU. So that's where it happens. So libvirt will work through that socket. And if you're doing test and development, you can use this shorthand, which is just a sugared form of the long, lengthy command line above, the -qmp Unix, and you provide the socket and a bunch of other options. So that's handy there. So now that you've set up a launched QEMU with a socket, now you can connect to that socket. There's different ways to interact with the QMP monitor. This is a bit tedious, but can show actually what is going on, is the socket cat utility. I invoke this socket cat utility to connect to the Unix socket that we just launched with QEMU, and supply the readline library option so that it caches the history of commands that I type. At first thing, it gives out, it says, hey, connection is successfully established. So that's the greeting message it shows. So that's a good indication. After that, you have to explicitly specify this command called QMP capabilities. That is for negotiating different capabilities in case. So far, there hasn't been any use cases for it, but there is apparently a new feature on the list, a mailing list, that uses this. But for our purposes, what's important is that it is mandatory to specify this capabilities flag. And then you're ready to send and commands, receive, query, arbitrary commands that you can send. So regular QMP commands. But you don't want to type manual JSON commands unless, I don't want to finish that sentence, but so yeah. But thankfully, that's where libvirt comes to rescue to automate this all and provide a convenient wrapper. So, and there are other ways to interact with QMP monitor. I mentioned this for completeness sake, and also some of the examples that I show, I'll use the first one. First is the QMP shell that lives in the QEMU tree, source tree, where you can just, it takes key value pair so that you don't have to type out long, lengthy JSON commands. So that's convenient there, right? So it lives in the tree. You just apply a verbose parameter and a pretty print one so that it also prints out the raw JSON if you want. And supply the path to the socket that you launched QEMU with. So that's a convenient one. I'll be using this to show some examples in the next slides. And the libvirt also offers a QEMU monitor command via its shell interface through which you can type JSON. But again, that's only to query. Now here is a caveat that you don't want to modify the virtual machine state behind libvirt's back, because then you get to keep the pieces if it breaks. So it's useful to only query, but not to modify the virtual machine state. So in this part, we'll quickly see a glimpse, actually, at what block devices, how block devices are configured in QEMU. So QEMU's a block device has a notion of a backend and a front end, where a backend is you can configure a block device and set up various things like specify cache options or specify formats and change backend file and various other things. It does a fine-grained control that it provides. There's two different ways to configure it. One of them is legacy, but still libvirt uses that. And the more recent changes are done via the -blockdev command line. But we won't get into that. If you want more details, there's a talk. There's been several talks at KVM forums, previous KVM forums. From there you can refer. And also the other notion is a guest visible front-end device, like like a SCSI device or something like that. And that can be configured via a runtime using the device add or the -device command line. That was configuring on command line. So that's notion of the block device. Now we see quickly what it looks like on command line to configure block device. It's fairly boring. Usually projects like libvirt will automate this away, but you can see the complexity to get a sense of that. Here you're just attaching a QKauto device to a QKauto disk to a Verde block guest device. The -block device, blockdev, configures the so-called backend, and the -device configures the guest visible front end. Again, here details are at KVM forums talks, so we won't get into that. I just wanted to mention it for completeness sake. And lastly, on this part is the blockdev add, which is the runtime command line option. Again, fairly uninteresting, just run a simple JSON structured command to add a QCOW2 block device. What is nice here is, in these recent changes from QEMU's block layer, in the QEMU block layer, the command line equivalent of the JSON is just a 1:1 mapping of the raw QMP. If you kind of squint your eyes and look at the options on the command line, it's just a direct 1:1 tree-like mapping of the above. So that's the convenient way to launch, if you want to launch a QEMU instance by looking at some JSON existing configuration. Again, you don't want to do that by hand. Most of this thing is done by when you're doing testing and development and running from Git and so forth. So more details, previous KVM forum talks. Here we see the part that I want to talk mostly about, which provides various use cases. So the live block operations, there are several different of them. To get to any of them, first we need to quickly see how do you configure a backing chain. To that end, QEMU offers a couple of commands. Block dev snapshot sync is it creates a synchronized snapshot. But this is an older version. There's also a newer version of it called block dev snapshot, but that's more to do with configuring it a bit more easily with the recent changes. So what happens essentially when you do it is same when you do it when offline. When a guest is running, with a single disk, the existing disk becomes the backing image, and a new QCOW2 overlay is created to track the new writes from that point onwards. So the existing disk becomes read-only backing file, and all the new writes go into the overlay. So it's all live, and QEMU points the writes to the new overlay. So now overlays have to be QCOW2 format. Base images can be LVM, raw, block device, or any of the other formats. And of course, the appealing aspect here is that there's no guest downtime. The snapshot is instantaneous. Some of you here may have used QEMU's internal snapshots, which is more convenient because the snapshot and the delta, both of them are located in a single file. And that's nice to copy around and so forth. But it's not the most well-tested code path, and upstream concentrates more on these external snapshots, although internal snapshots are sometimes convenient. And there's a bit of a guest pause involved there as well. Not too long, but for some, it may not be acceptable. But the recommended upstream recommends this format. So to see a quick example, when you start with that base image where live QEMU is writing, you launch a bunch of the block dev snapshot sync, the synchronized snapshot command with a bunch of parameters. It will create the overlay. Again, nothing super exciting. And there's a libvirt equivalent of it. You don't have to launch via QEMU, QMP, right? So when libvirt provides nice virtual machine lifecycle management. So I wanted to highlight that. It's a simple, fairly command line. And the result would be that, where you see an overlay that's pointing to base. Now, earlier, the live QEMU was pointing at the base image. Now it's pointing to the just created QCOW2 overlay. However, to manage these long backing chains can get tedious. And not only tedious, but there can be I/O penalty involved. So, for example, when you have a long backing chain, there are multiple files to track, and I've even heard some cases where somebody using 100 backing chain a disk image, but I don't know what their use case is. So it can get really cumbersome, and also there can be I/O penalty. So if the cluster that QEMU wants to read is not in the immediate overlay, but somewhere in between, so it has to traverse through all the images and then pick that and then cache it. But there's some solution for that. First is the live disk image chain merge, where you have a long chain, and the problem is to merge that long chain to short. So the simplest solution is to merge all of them into the base image. So that's fairly simple, right? And how do you do that? You first run the snapshot command to create the 3 overlays, and then you run the commit command so that please commit all the content from 3 overlays back into the base. And then you finally complete the commit job and pivot the QEMU to the base. That's it. That's libvirt equivalent. Now, what is the result? The result is a single consolidated base image with all 3 images, content from all 3 images into the base image. The all intermediate images are invalid. So you can throw them away, a single image. So that's a nice way. And people also use this to make efficient disk snapshots. There's some wiki pages for that. We'll point to that later. And stream is is the second one in this series of 4 commands that I want to talk about. It's similar to commit. I don't want to go into details, but just want to mention for completeness sake. But it's safer in the sense that the intermediate overlays can be valid. Meaning, in stream, you're copying content from base images into the top image. So the intermediate images can remain valid. There's details on this. It can be overwhelming to grasp all of it in one go, but I just want to mention that. And the other interesting one is the mirror command, where you can synchronize the entire disk image chain to a target, where you can synchronize either parts of the chain or the full chain or only the top image. So that's the operation. I'm showing a bunch of QMP commands. So it's saying, please copy all the content from all the chain into a target image called copy file, and complete it, and optionally turn the live QEMU to that copy. So now that we mentioned that, this can be combined with a new, another concept called NBD server. QEMU has a built-in network block device server where you can export disk images that are while in use. It has a bunch of commands. So, and you can combine the just mentioned mirror command with NBD to solve an interesting use case called live virtual machine migration without having to set up shared storage between 2 hosts. So fundamentally, under the hood, that's what is happening. QEMU runs the mirror command, a variant. There's 2 variants, but we don't get into that. But it essentially runs the same mirror conceptual command. It copies content from source to destination. The destination sets up the network block device server, destination QEMU, and exports a pre-created disk image and copies all the contents to there. So the more details are at the bottom. So on this slide, you see what all I mentioned from QEMU, the equivalent libvirt automation. So it's just a command for completeness sake, and if you want, you can try this out later. And projects like higher level management tools like OpenStack use the equivalent Python APIs of libvirt to do the same things. This is the last primitive. Again, it's a bit similar to mirror command. For mirror, the point in time of a copy is when you end the synchronization of disks on the source by issuing the block job complete command. And for backup, the primitive that you see at the top is when the point in time is when you start the operation. Again, this can seem subtly same, and there's ways to upstream at least is thinking to merge most of these into a couple of common commands. So, but yeah, at the moment, it seems a bit similar. And the interesting thing here is it has an extra synchronization mode. Along with copying the entire chain and so forth, it also offers an incremental flag that is useful for incremental backups. So for that, there was a talk at FOSDEM last year, so you can refer to that one, and it has more details. Just like how we combined the mirror command with NBD, you can also combine the backup with NBD for other use cases. One of the things that I hear is if you want to examine guest I/O patterns without by an external tool, so you can simply copy the entire chain, or only the current writes. Actually, no. When you're examining guest I/O patterns, you want to see the current patterns, and you can say, hey, please only sync all the current writes to the copy on a destination, and you can examine them. Apparently, some virus scanners or other such use cases are there for that. So yeah, there's that. in summary, there are 4 of them: commit, stream, mirror, backup. 2 of them are a bit similar, and there's a lot more details in the links that I showed below, which has examples and other things that you can refer to. So if you have, this is the reference slide that I mentioned, which has links to other KVM forum talks, which you can look at the gory details of QEMU if you're interested. So, any questions, if there are any? Okay, so I totally confused everyone then. Thank you.